It is Pi Day 2026. That means it is March 14, 3.14 in American date. So, like usual, like Pi Day tradition, we're going to calculate pi. And this year, I decided to calculate pi using some constant that we already know, but we can still calculate it, measure it by hand, g. So let's talk about that. How would we calculate pi using g? Well, we'll talk about it later, but let's look at g for a second. How would we calculate g? By measuring it or by just finding it out? Well, there are a few ways to calculate g. For instance, the classic equation g is equal to gn over r squared. We can use this to calculate g. That works, but I don't know the mass of the earth, and I don't think I'm looking to measure the mass of the earth. I mean, we probably can. I don't think I can. And the radius of the earth, I mean, there are ways to calculate the radius of the earth, but I don't know how to find the radius of the earth. And the big G, the gravitational constant, I mean, Newton knows how to find that probably, or was it someone else? I don't know what the big G is, so we can't use this. Alright, what else? Well, we have this pesky little equation. G is equal to 4 pi squared L divided by T squared, which is nice and all. In fact, as a matter of fact, you can use this equation to find what pi is, you know? But we can't use it to find g because there's already pi in it. So we will use this equation to find pi. Let's just mark this for a second. We'll use this equation to find pi using g, and that is exactly how we're going to do it. And I will get to where this equation comes from and what L and T are. This is basically a basic pendulum. We'll get to it later. Right. And well, we also have an equation that Galileo himself kinda came up with. G is equal to 2 by t squared, and we are going to use this equation. We are going to use this equation to find g, and you might ask, oh, what is this equation? Well, this is the free fall equation. If you drop an object from height h and it takes t amount of time to fall, then g can be calculated from that, and we're gonna derive that. We're gonna figure out where this comes from, and we're gonna measure what g is by measuring the height, measuring the time taken for it to fall, and finding out what g is. So basically, our method is simple. We're gonna have an object, and we are going to drop an object from a set height, measure the time taken for that to fall, and then plug in here, find g, repeat a bunch of time, you will get g. Right. So how do we even get this equation in the first place? What is this? I just pulled it out of my ass. Well, no, you can derive it really easily, and let me actually derive it for you. This is the fun part. Like, I'm a math channel. Come on, I mean, this isn't a math channel. We're on LygerScience. This is gonna be science stuff, but behind science is mathematics, and so we're gonna be doing some mathematics first of all. Right. Let us define what g really is. What is g? G is the acceleration due to gravity. It is how much objects accelerate when gravity is pulling it down. So, what is acceleration? You might ask. Well, acceleration is basically meters per second squared, aka it is how much the velocity increase every second. Basically, how many meters per second does it increase every second? It is meter per second per second. So g is around 9.81 meter per second per second. The velocity of an object falling is increasing by 9.81 meters per second every second. So let's just take 10 for example. Then that means that at 0 second, velocity is 0. 1 second, velocity is 10. 2 second, velocity is 20. 3 seconds, velocity is 40. And the velocity keeps increasing by 10 every second. 10 meter per second per second. That is what g is. So, by the way, 10, I just pulled it out as 9.81. I don't know what 9.81 is. That is what we're gonna measure. That's the fun of it. So, let's define g. G is acceleration. Let's define acceleration. Acceleration is basically how fast something's speed change. So basically, acceleration is the rate of change of position, because acceleration is the rate of change of velocity, and velocity is the rate of change of position. That means that acceleration is the rate of change of position. Let me write that down for you. A is equal to d squared, second derivative, s over dt squared. There we go. Which, again, like I said, acceleration is the rate of change of velocity, and velocity is the rate of change of speed. This position, let me just write it down here for you to see. A is equal to dv over dt, and v is equal to ds over dt. That is where we get this from. And if we substitute acceleration with the height of something falling, acceleration with g and s with the height of something falling, then we get g is equal to d squared h over dt squared, and we got it. This is our basic formula. But LygerScience, this isn't anything similar to g is equal to 2h by t squared. Where did that come from? We'll get to that later. We will first put this aside. We will use it later. First, let's look at this formula for a second. What can we do with this? We can, take this and we can integrate both sides. So we get the integral of, let me just write it down so that you can see here clearly, d squared s over dt squared is equal to integral of a. I'm going to integrate with respect to t, of course. Should I write it down? Dt equals to integral of a dt, and these are going to cancel out. This square and this is going to cancel out. So we're going to be left with, this is going to cancel out. We're going to be left with ds over dt is equal to integral of a dt, that is just at. And of course, don't forget the integration constant plus c. We actually have a plus c here and a plus c here. They can combine to make 1 plus c. Don't need to worry about the details. Right, let's look at this for a second. What is the rate of change of position? We already found it out. The rate of change of position is velocity. Velocity is basically how much position is changing. So we can substitute it in here. V is equal to at plus some constant. Wait a minute, that sounds awfully similar. V, we can think of it like the current velocity, the current final velocity that we have. Acceleration is how much an object is accelerating, and t is the time. So if you multiply acceleration by time, you will get the increase in velocity, aka the change in velocity. So if you think about it for a second, then you have final velocity v, change in velocity at. That must mean that c is the initial velocity, and it will make more sense if I write it down here. So instead of writing it down, I can just write down at plus, I'm going to write down u as my initial velocity. If you think about it, if you have an initial velocity and you add some velocity change to it, aka you have an initial velocity, you accelerate from that velocity for some time, then you're gonna get the final velocity. Does it make sense to you? Look at it for a second. Initial velocity plus change in velocity is equal to final velocity. And the change in velocity is basically you are accelerating how many meters per second for a set amount of second. How many meters per second are you adding on top of your initial velocity? And look at this. This is our one of the basic kinematics equations. There you go. There you go. Just algorithms right now and again. The whiteboard isn't really the best. It is interfering with my watch because they're both electromagnetic waves. There you go. Good enough, whatever. So there's our equation. Well, there's an easier way to derive this without calculus, and I will help you do it. Well, the easier way is to start from the definition of acceleration. This is a nice definition of acceleration. I like it, but it could be better. Acceleration is basically how much speed changes over a set of time. Let's write that down. Acceleration is basically how much the speed changes over a set amount of time. So basically, how much does the speed change? The speed changes from final velocity to initial velocity. Initial velocity to final velocity. If you want to find the speed change, then you subtract the final from the initial. So v minus u over t. That is our definition of acceleration. A is equal to v minus u over t. You multiply t to both sides. Let's distribute terms. We get at is equal to v minus u. I want to isolate v, so we're gonna get v is equal to u plus at. And would you look at that? These are the exact same equation. So it doesn't matter whether you take this route or this route, whether you do pesky calculus where you integrate, or whether you take the definition of acceleration, you get the same equation. Who would have known, who would have thought that physics works in both ways? Well, now that we have yapped a lot about to get one of the basics equation of kinematics, we can move on. We can move on to finding acceleration. Let's do that. Let me actually write down it in the middle so that everything becomes clear. Let me just wait and then wait. There we go. Let's start by taking this equation. You know what? Let's forget about it. Let's take this and then start a new page. It's cleaner that way. There you go. Let's take our equation. V is equal to u plus at. Let's bear in mind one of our basic equations. A is equal to dv over dt. Therefore, if you want to find A, you can differentiate v, and v is equal to ds over dt. So if you want to find v, you can differentiate as the displacement. What if we want to do the other way around? What if we want to find the displacement? How would we find the displacement of it? Well, we can integrate. The opposite of taking the derivative is integrating. So we can find the displacement by integrating velocity, and we already have a velocity here. So we can integrate both sides to get the displacement. So what we're going to have is integral v dt. We're again integrating in respect to t. We get integral u plus at dt. We're going to get distance here. This becomes ut plus this becomes at half at squared. So yeah, I think some of you are starting to see that this is very familiar. Again, integration constant plus c. So basically, we have the final distance, we have the change in distance, and then we have our integration constant, which is basically where we start from. In this case, I'm going to start throwing things around from 0. Wherever I throw things, I'm going to assume that that throwing line is 0. So if I drop something from this height, this is 0. If I drop something from here, this is 0. If I drop something from here, then that it will be the 0 line, right? That will be 0 to wherever it drops. So we're going to ignore that c plus c because you can literally take it to the other side, take this to the other side, and that will be like the net distance that it falls, and we can calculate that. And voila, this is another one of our kinematics equations. S is equal to ut plus half at t squared. And now we can finally put in our g and our s. Well, before that, let's take a look here. U is our initial velocity. And we're going to be dropping things. We're going to be just releasing them like that. We are not going to be throwing them. We're not going to be throwing up like that. We're not going to be throwing it like that. We're not going to do that or do that. We're just going to be simply dropping them. So the initial velocity that we put into the object will be 0. So this thing will just be 0. And then what we're going to be left with is s is equal to half at squared. And now we can put in our things like our gravity. So s is basically the distance it falls, which is going to be height. A is going to be g, our gravitational constant. Well, not gravitational constant, that's a big G. Our gravitational acceleration. And then t squared is the amount of t, the amount of time it drops, divided by 2. Rearrange this, we finally get g is equal to 2h by t squared. And there we have it. This is going to be our gravity. We're going to find gravity like this. Yeah. So how will we find gravity? Scientifically, like using actual scientific methods. Well, I have written a document on procedures. We're gonna need an object. First of all, I'm gonna put it on screen here. You can see. We're gonna have an object which should be heavy. I am going to be using an apple. An apple is perfect for something like this because Newton discovered gravity because of an apple, which is wrong, by the way. It's a myth, but let's pretend it's true. Newton invented gravity because an apple fell in his head. So we're going to be using the same apple. And then we are going to need a measuring tape to measure the height to drop the apples from. And we're going to use a stopwatch, aka our phone timer, which works perfectly fine. And then we're going to use a release board, aka a table. We're going to use a table, drop it from the table. So basically we're measuring the height of the table. And then we're going to have a hard floor so that we can actually hear the thud, the top sound that the apple makes. Or in this case, if it is a pen, you can hear the sound it makes when you drop it, like that sound. We're looking for that sound. And once you hear the sound, you hit stop. And by you, I mean me. I'm gonna have to hit stop as soon as I hear the sound. And I'm gonna have to hit start the timer as soon as I release. I can't throw it, I can't do that. Release, because U is 0 here, nothing here. And the procedure are as follows. We use a measuring tape to measure the height around, I wrote it here, 2 meters, but however tall the table is. And then we'll repeat it using higher and higher shit. And then we're gonna make sure that the bottom of the apple is aligned with the measuring tape. We're gonna have to time it perfectly. I mean, we're all humans. I'm human after all. There's gonna be some timing mistake. There's gonna be some reaction error. It'll be fine. And then we're gonna do it 5 times. And then we're gonna do it 5 times again, so a total of 25 times. I think that should be enough. Or 50 times. You know what? Yeah, sure. We'll do it 50 times or 100 times. We just want a very, very accurate value of G. It won't be precise. It'll just be accurate. To get precision, you need high, like fucking laser, light gates, whatever. Anyways, um, we need to have some control variables. We need to release it the same way, and the way to do it I will demonstrate it in the lab, and by lab I mean my room, of releasing the apple from the table, from the height of the table. Just open your hand, and then we'll have to make sure that the room is quite sealed and not ventilated, so that there is no wind and air resistance is as negligible as possible. And always measure from the bottom object, and then we'll use this pesky formula to calculate G. It'll be fine. Right, well, we'll see you in the lab. Hello and welcome to my lab. Well, this is my room. Of course, we have the epic Romanian flag here, and my lab is basically just my room, but whatever. The way we're gonna do this experiment is we're hoping to use this bad boy here as our kind of measuring tool. Well, actually, we do have a measuring tool. We have a measuring tape here, and we're gonna measure the height of this bad boy, and we're gonna be dropping apples all day long. Hopefully the neighbors downstairs are okay with it, but yeah, we're gonna be dropping from different levels, recording their different times, and basically, yeah, and then we'll put that in a data sheet there. We'll process the data by removing anomalies, taking averages, etc. But yeah, let's do it. This is a goddamn good apple. So we're gonna be using a phone timer. Wow, why is it so sweet? Jeez. So, anyways, we're gonna be getting a random apple, and we're gonna start from maybe the lowest level, and then we're gonna go up to the top slowly. And we're just gonna drop them off by. So let's do a test run. We're just gonna start a timer as soon as the apple falls. So let me just put this inside here. Doesn't affect, yeah. So when I touch this, I start the timer, and when I hear it hit the ground, I'm gonna stop the timer. So there you go. That is good. That is good enough. There is some inaccuracy, of course, between me hearing the apple drop, and also some delay from when I actually push it off. But you know, human errors. We're trying to calculate pi to the nearest one digit. If I get pi is equal to, like, let's say 5, that is good enough. Well, actually, this is experiment number 1. We're actually calculating G first, and then after G we'll calculate pi. So let's get started. So first we're gonna try doing about 10 trials on this level. So let me just measure how tall this is. Did I cut myself? No, it's fine. I don't know how to use a tape measure. Jesus Christ, let me just go over here. 89.2, sure. 89.2. I'm gonna put that in my data sheet. 89.2. Well, not 89.2, it's gonna be 0.89892. And then I'm going to copy paste that. I didn't screen record this for sure. I don't really care. Copy paste this about 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9 times. There you go. And then we're gonna time those. Right. Well, let's get started. We're gonna use the same apple just to eliminate any bias. And we'll get started here. We'll make sure the apple's absolutely on edge. I'm gonna start the timer. You can follow along at home if you want. This is a very easy experiment to do. Okay, about 0.28 seconds. All right, let's try it again about 10 times. I'm gonna speed this up so you can see. Um, skip ahead, basically. Yeah. Right. I have recorded 10 data points, and there seems to be some anomalies, which I am going to show you. But it is on screen right now. Interesting. Such interesting. Okay, well. This is a lot worse than I expected, which is why we are going to try to do the experiment one level higher, because as we increase the time fallen, that decreases the percentage uncertainty, because we have the same uncertainty time. Like my reaction time, human reaction time for this timer is the same regardless of how long the apple falls. So the longer the apple falls, even though my reaction time is constant, the apple is falling longer. So if you find the percentage uncertainty, then there's going to be less percentage uncertainty as the longer the apple falls. I already explained this in the lab. I mean, in the whiteboard. So we're gonna try that one level higher, and let me just quickly edit this out. All right, let's go one level higher. All right, let's go one level higher. And the time, let's measure the height of this. Let's not mess this up. Mine's about 134. I was wrong. Parallax error. Make sure to read parallel to the scale. Don't read it from top here. Make sure to read it like that. It's actually 134. It looked like 133.5. So we're gonna enter 134 in here, 1.34 into our data sheet. Copy that, paste it a bunch of times, 9 times. There we go. And let's measure how long it takes for the apple to fall. We have bad news, guys. The apple split. Oh. Well, what do you know? If you keep dropping apples, they're gonna break. And it made a huge mess down there, but we'll be fine. We'll just use a new apple and we'll continue our experiment with a new apple. It is slightly kind of unfair that oh, there's a mess down here. It is slightly unfair because the messes have changed, but theoretically, gravity should not matter depending on the mass. So what does matter is the air resistance, and air resistance kind of is affected by the shape of the apple. So there is going to be a slight unfairness, but it's fine. All apples are very similar sized anyways. Let me find a bad apple. Can we get a bad apple? No, all the apples are pretty good. What is the worst apple in here? You're pretty bad. Okay, let's keep on doing our experiment. Okay, we have gotten 10 data points. There seems to be no anomalies this time. They seem to be about 0.35 and 0.36, 0.34. So that is a good thing, isn't it? That is a pretty good thing to be good of. Let me just quickly. Right, let's move on by making another table like this again, and let's move on. So let's move on, and this time we're gonna go one level higher, all the way to up here, and let's measure the height of this. (168). That is the height of that. That is 168. Let me just put 168 in here. 1.68. Copy paste that a few more times. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. And now we can measure gravity in that 168 centimeters ball. Well, it did it again. Exploded. But oh well. Is this what apples do? Like, are apples like just designed, like they evolve to explode so that they scatter their seeds all around and make a mess? Time for a new apple. An anomaly, huh? Or 7. And the apple split on the last drop, which is nice. but now there's apple juice all over my house, and also there's seeds everywhere. Well, hello there. We are in our data analysis lab, and as you can see here, we have our three different experiments. Our gravity value was calculated using 2 times the height, average of the height. Well, I mean, all the heights are the same, so you don't really need to even take the average. But 2 times the height divided by time squared, where t is the time squared, where we took the average of the time. And we are doing the same thing for all three of our experiments. And so we have three values of d which are very off. I'm going to clean these up by removing some anomalous data. For example, here we have like, I think this one may be anomaly. Yeah, this one is definitely an anomaly. Things like that, I will clean that up. Here there is no anomaly here, so that's good, I suppose. Here there is this guy anomaly here. This guy too. So I will redo these experiments, and hopefully we get a better value of g. So for now, let's find the average value of g, which is gonna be the average of these three values. There we go. And that gives us 19.68. So there we have it, guys. There we have it, chat. I guess thanks for watching. We have found gravity. The value of g is equal to 19.68. It is more than twice, more than double the amount of the accepted value. But who knows? You know, this might be the real value. So yeah, we will continue on to doing experiment number 2. I will see you back in the classroom. Welcome back. Now that we found g, we are going to use it to find pi, because it's pi day after all. Let's not forget, we are doing this on pi day. We're calculating pi. G is just one part of our equation. And now that we have half of the video done, we only have the other half to go through. We have one more experiment coming up, which we're going to use the second equation that we showed earlier. But we're going to have to prove that equation and make sure that it really works. So, what was that even about? What was that even about? We had some square roots and capital T and capital L. What are those? Those are pendulum measurements. Capital T is the time period of the pendulum to complete one full cycle. So if you start from the left side, it should come here and then come back there. That is the time period, basically how long it takes to get back to its original position. That is the time period of the pendulum. And then L is basically the length of the pendulum, basically. So if you have a pendulum like this, well, this is a very bad pendulum, but we will do the experiment and you will see what a real pendulum looks like. But first, before we do that, we gotta make sure we understand what the equations are. So let's draw a pendulum. Let's just use this for a second. Let's draw a pendulum, right? We have our ceiling, we have our baseline, there we go. And then we're gonna have our pendulum swinging to the side, like so. Oops, that is way too not straight. Nope, that's not straight either. There you go, good enough. It's gonna be our pendulum. This is basically L. That is L. Similar to how this is also L, because this is like before it swung, it was here and then it swings up to here by an amount of like theta, let's suppose, by a distance of s. Right. We'll get to that later. And then let's see what the forces are in here. We have the weight of the pendulum pointing downward, and then the force of the pendulum wanting to go back to its equilibrium position. By the way, this is the equilibrium position. We call it the equilibrium position because it is what it eventually settles to, right? If you have a pendulum that is swinging for a long time, it will eventually settle to here, this equilibrium position, stable position. We also call it a stable position. So there is a force that wants to go back to its stable position. Let's call that force F. And then from here, we can draw some basic trigonometry. I'm not going to go into details for trigonometry because I kind of also suck at it. But basically, if you have a 90-degree horizontal force here, then this piece here is theta. And then we can draw a quick triangle on the side here. We have something like this. This is mg, this is f, and this is theta. And if you're wondering how this became theta, you can translate, not even translate, you can transfer this here by using similar triangles or just basic geometry. I'll show you on this side here, down here too. You have this giant thing, which is theta, and then you have this, which is perpendicular to that. This is 90 degrees. This was also 90 degrees. I don't know if you can see clearly. And then this is mg. This is f. You want to find what this is. That is basically theta. This part is theta. And you can do that by taking this as 90 minus theta. So this part right here. Can I change colors? I can change colors. Yeah, good enough. This part right here will be 90 minus theta because this is a right triangle. You see? Theta, 90 minus theta. And oops. Because of that, then this will become 90 minus theta because this is a right angle triangle. I think you can see. If you don't see, draw this in your notebook and then you'll be able to see it more clearly because this is a small drawing and I don't even think you can see it on screen. But yeah, this is theta. So from here, we know that f is equal to sine theta mg. So let me just write it down here. F is equal to mg sine theta. Well, not quite, because theta actually is turning this way, and we're assuming theta is turning this way. And if you look at it, the way theta is turning is away from the origin. Force is going towards the origin, aka the force is acting against theta. Basically, the force is going in the opposite direction of displacement, basically. So we can kind of rewrite this as F is equal to negative mg sine theta. If that makes sense. Just if it doesn't, just kind of try to absorb it in for a bit. We have theta, which is the displacement going towards one direction. Let's suppose left. F is going to try to go to the right direction to go back to the origin, so it'll have to be a negative sign there. But yeah, don't worry about it. And then sine theta. How do we even calculate sine theta? Well, that is something hard to do. So we're engineers after all. Because we're engineers, we're gonna approximate sine theta is approximately equal to theta. Because why not? So we can replace this as F is equal to negative mg theta. There we have it. Perfect. Where do we go from here for now? Well, I'm gonna leave this as it is. For now, we are going to go into one more thing. I forgot one more thing. Let's look at this for a second. This is a piece of sector that looks something like this. Like that. This is L. This is L. Okay, never mind. It doesn't look like L. Just draw everything again. There we go. This is L. This is L. This is S, this is theta. From here we can conclude that S is equal to L theta. S is equal to L theta. And from here we can substitute theta to here, so we get F is equal to negative theta is equal to S over L, so mg times S over L. And basically, yeah. Right. So we'll leave this for a second here. We're gonna go to this side of the whiteboard and we're gonna do some circular motion, more specifically harmonic circular motion. And harmonic motions are a bit weird. They are difficult to grasp. They are kind of counterintuitive to understand. So I will try to be as generic as possible. I won't go into details. If you want to know the details, you can go on to watch 3 Blue 1 Brown's video. He has a really nice video on circular motion, or any other physics channel, physics mathematics channel, you know what I mean. So first we need to look at what a circular motion is. If you have an object rotating around some planet, let's say we have got the sun here. The sun is way too small. Let's say you have the sun here. Jeez, this is a really shitty whiteboard. And you have some object, like let's say the Earth. Which is rotating. Oh my god, this is horrible. There we go. Which is rotating around like that. Then let's say this is r radius apart. It is actually independent of r, of like how much it rotates. All we care about really is the angular moment. So if this is the initial position, and let's say this is the final position of the Earth, then this angle here is all that matters. We're only caring about the angle, aka angular speed. We only care about the angular speed of how much it rotates. Because think of it like swinging a rope around you. Like, you know, like having a rope and swinging it around you like that, or either like that or like that. It doesn't matter whether you swing like this or whether you swing like that. What you're gonna have is you're gonna have you, oh my god, in the center, and you're gonna be swinging that rope around you. It doesn't matter where the object you're swinging. It could be here, it could be here, or it could be here. They're all going to be traveling by the same angle. I don't know if you notice. I don't know if you can see clearly. Basically, it is independent of the radius. We're looking at angular speed here. It doesn't matter how long the rope is. It doesn't matter how far the object is away from you that is rotating. We only care about the angle itself. And one full rotation is 2 pi. We know that. So we write 2 pi here. And we're gonna assume it takes a period of t, capital T time, to complete that. We call this omega. This is not a W, this is an omega symbol. It looks like a W, but it's not. And this is called angular speed. Basically, angular frequency, if you want to call it that. But it's angular speed. Or, yeah, whatever. Yeah, again, terminologies. These are physics terms. People call them different things. But basically, we're going to be working a lot with this in this section of the video. We're going to be using that a lot. So be familiar with the guy, little guy. This little guy is responsible for the Earth rotating around the sun, or you swinging a rope with something attached on the end. Doesn't matter how long the rope is, doesn't matter how far away the planet are from the sun, angular velocity is all we care about. How much of the angle it changes per time, basically. So 2 pi is the total circle that you go through. T is the total time taken for that circle to go through, the time period, aka how long does it take for you to come back to your original position. And you may be wondering how this relates to pendulum, because pendulum are not circles. They don't go one cycle around, do they? They do. Well, if you look at this little animation I pulled off Google, you can see that actually circular motion, circles, are just sine and cosine waves. Well, the cosine wave is going upwards and also flipped, but you get the idea. If you flip it around, it's the cosine wave that you're all familiar with. Here's another animation where the cosine wave is looking better, but see, every circular motion can be translated into a pendulum wave motion, and vice versa. If you have a pendulum wave motion, then that pendulum can be modeled as a circular motion. A pendulum swinging in your grandfather's clock is no different from the earth rotating around the sun. They're all circular motion. If you drop a stone in a puddle and it creates waves around the stone across the puddle, that is circular motion, whether you agree or not. So, circular motion. We're going to be dealing with this guy a lot. Let's take this guy, and what we're going to do is we're going to find the distance that this guy travels. I hate this. But yeah, we're going to find the distance. Let's say S. I'm going to do it around here, below this guy. So the distance it travels is actually going to be given by A sinus of omega t. This is the equation. How do we get this equation? Good question. Look at this animation. That is how we get the equation. The up and down displacement is basically a sine wave. It is a sine wave. Up and down motion of a circle is a sine wave. So if you look at the Earth from the side view that I'm looking at, it is a sine wave. If you look directly from here, from your perspective, it will be going in a circle like that. But if you look at a circle from this perspective, it's an up to down motion. So that up to down motion is a sine wave, and we can find the amplitude of the sine wave, which is A. This is the amplitude, by the way. So the amplitude of the sine wave, basically the amplitude of the circular motion, simple harmonic motion. This is the same as a spring bouncing on itself, by the way. If you have a spring, you attach a mass to that spring, like spring here, attach a giant mass on here, and you bounce it like that. Same equation here. This is a sine wave. It's a sine wave with some amplitude and some constant to the time. Yeah. So this is just the basic that we need to know. This is where all the bullshit ends, and from here it's just mathematics, no more physics. Let's differentiate this to get velocity. Differentiation time. V is equal to, you differentiate this, what do you get? You take the omega outside, we get A omega cos of omega t. Nice. Acceleration time. A is equal to differentiation again. Take it out, cosine becomes negative sine. So I'm gonna write a negative in the front. Negative A omega, that means omega squared. Sinus, negative sine of omega t. Wait a minute. Let me just rewrite it like this. A is equal to negative omega squared A sine omega t. Wait a minute. Look at this. Distance distance is equal to a sine omega, sorry, displacement. Displacement is equal to a sine omega t. Acceleration is equal to negative omega squared times a sine omega t. These are the same exact equations. What? So that means that we can just replace that. So what we have here, we have acceleration is actually equal to, whether you like it or not, acceleration is actually equal to negative omega squared times the distance s, and there we go. We have proven this equation here. Acceleration is actually equal to negative omega squared times displacement, where omega is the angular velocity. Acceleration of an object going in a circular motion, either in a pendulum or a swinging rope or around a planet or a bobbing up and down spring mass system, whatever system you're using. If you throw a rock into a puddle and make a wave, acceleration is equal to the negative angular velocity squared multiplied by the displacement. That is the equation we need. And with that equation, I can conclude yeah. Put it in there. So let's do that real quick. I'm kind of tired, but let's do that. I'm not tired. It's just that we did the experiment first before recording this video, and the whatever. Let's do that. F is equal to ma. We all know that F is equal to mass times acceleration. Ma is equal to actually negative mg s divided. Ma is equal to negative mg s divided by L. Metal gear solid divided by liquid. Metal gear solid divided by liquid. Ma is equal to mgs divided by L. We can cancel out that. We can put that in here if we want. Shall we? Sure. We're gonna get, let me just write it down here really quickly. Take out the a, we get a, sorry, take out the m's, we get a is equal to negative gs. Why is this so hard to draw this? Just a second, just give me a second. I'll fix this, I promise. There we go. Divided by L. And this is GS divided by L. Okay, we have this here. We have that there. I'm going to put this in here. So what we're gonna have is negative omega squared s is equal to, because a is negative omega squared, okay? Negative gs over L. S and S cancel each other out. We have negative omega squared, which is again this thing squared. So negatives also cancel out. Negative cancel out. S cancel out. So we're basically dividing each side by negative s. We get 2 pi over t. I mean, this is where pi comes from, because one full circle of a circular motion is 2 pi. That is where pi comes from in our equation. Pi just appears out of nowhere, right? Yeah, amazing. The whole square is equal to g over L. I think you're already seeing where this is coming from. We have 2 pi. I'm just gonna skip all the steps. What we're gonna be left with is I'm gonna make pi the subject because we're trying to find pi. We already have g, we found g. We have pi is equal to, so we have square root of g over L, and then we have t over 2. I'm gonna multiply the t over 2 into here, so we're gonna have t over 2 square root of g over L. That would give us square root of 4g over lt squared, I suppose. Something is wrong. What went wrong? G or L. Yes, everything's. Oh no, never mind. I'm correct. I just wrote it weirdly. Yeah, never mind. So I was saying it correctly. I just kind of this becomes t squared. So we have gt squared. This looks like a 9. It should look like a 9. Gt squared divided by 4L. And let me just rewrite this. You can try this at home and follow along if you want. There you go. This is gonna be our pi equation, and we got it. What? There we go. This is it. This is it. This is literally it. Pi is equal to square root of gt squared over 4L. And it can't get simpler than this. So we got g. We've measured g. Because we measured g, we can then do another experiment with a pendulum. We're gonna swing a pendulum around, measure the time period of the pendulum to get back to its original position, and then we're gonna find the length of the pendulum, and we can plug it into our equation. We got pi. We repeat it like 5 times, 25 times, 50 times. We'll get pi pretty accurately. And you're gonna be wondering how we're gonna find a pendulum. Well, we're gonna use the same apple we used for the first experiment. We're gonna use an apple, tie it to a rope, stick it up somewhere up there in my room. I mean, in my lab, and then measure the length of the string, measure the time period for the apple to go back to its original position, 1 cycle, and then we're gonna calculate pi from that. Isn't it amazing? So there are some problems with that. The problem is that this is a problem. We're engineers. We just set sine theta is equal to theta, which it isn't. It's only true when theta is really small. And by really small, I mean really small. Well, not as small. We could probably have it accurate to 0.01. Have this accurate to 0.01 if theta is less than 15 degrees. So if we swing it below 15 degrees, maybe 10 degrees, maybe 12 degrees, maybe 5 degrees, I don't know, 5 degrees is too small though, because then we won't be able to tell. Maybe about 15 degrees-ish, 10 degrees or 15 degrees-ish, then it will be accurate to 0.01, and if it is accurate to 0.01, it's good enough. Like, I'm really hoping pi would be between 1 and 9. I just want the magnitude to be correct, right? I don't want pi to be turned out to like 10,000 or 3,500 or 0.005, right? I just want pi to have the correct magnitude between 1 and 9, and that is good enough for me. So the accuracy of 0.01 is already good enough for me. So we're gonna swing it about 15 degrees, and if we do just one swing, it will be inaccurate. There's gonna be human errors, and it's gonna take about 1 second to swing it. We'll talk about why it takes about 1 second to swing it. 2 seconds actually. It will take about 2 seconds to swing it, and so 2 seconds, meaning that if you add up reaction time to that, then that gives us so much, what do you call it, like error rate, percentage error, percentage, I forgot the word, uncertainty. Percentage uncertainty is going to be high. To reduce percentage uncertainty, what we're going to do is we're going to let it swing about 20 times, find a time for 20 swings, divided by 20, we get 1 time. And then basically what we're doing is instead of doing this, so this is the timed swing, and then we're gonna have some reaction time. How does this work? We're gonna have some reaction time here, reaction time. We're gonna have some reaction time here, like basically human error. Instead of doing this where the total percentage uncertainty is high, instead of having a high uncertainty, we are going to have like basically this. Just ignore it. Let's just say this is 20 times time, and then we're gonna have our reactions be here, and the reactions be here, basically like that. Instead of having like this, we're gonna have like this. So if you calculate the percentage uncertainty, this has less percentage uncertainty than this, because the reaction time is going to be the same. Me starting a timer is gonna have the same reaction time of starting a timer, regardless of if we're measuring 1 swing or 20 swings. So let's just measure it for 20 swings, divide by 20, we get 1 time period. That's how we're gonna do it. So let me just explain the procedures. I'll have it on screen here. We're gonna have a string as our pendulum, and then we're gonna have the bob is gonna be the apple, and then we're gonna pivot it somewhere. We'll think about it later, and then we're gonna have to measure the length of the string. We need a stopwatch, which is gonna be our phone. We're gonna have to set the length to be about 1 meters. Should be fine. I'll explain why 1 meter. And then we're gonna pull it back about 10 to 15 degrees. If we do it wider than that, this fails, the whole thing fails. And then we're gonna swing about 20 times, count 20 oscillations, basically how many times does it complete one cycle. One cycle is basically when the apple gets back to its original position. Calculate the time period, divided by 20, and make sure that the angle is consistent across different repetitions, and make sure to do this indoor because we don't want wind. Make sure that the pivot is rigid, and then we're going to put it in this formula: time, period, and then length. We already have g, we're going to find pi. And so let's do that. Hello and welcome back to the lab, and I'm here, Lab Ligers, in my closet because that's my lab. But yeah, don't mind my closet stuff. We're gonna use the closet hanging thing, the hang pole, to measure the oscillation frequency of that apple over there. Well, actually, it doesn't matter whether it is an apple or whatever mass it is, as long as the pendulum is in tension. The period only depends on the length of the pendulum and it has no relation with the mass of the object, which is exactly the same as experiment number 1, where in experiment number 1 we did not care about the mass of the apple at all. We didn't even need the mass of the apple to be consistent. We just kept letting apples fall, and then we calculated g, but this time hopefully we get a better answer. We're not going to, but let's just pretend we do. So first thing first, we gotta measure this length of our pendulum. Let's get this to stop swinging. There we go. And we can actually measure from where it swings. So like you gotta measure it from like the center of its circular motion. And from there you have to measure all the way to the center of the mass. So the center of the apple, not the string, not where the string ends. You gotta measure it to the center of the apple. And it looks like should be about I don't know, I can't really tell where the center of the apple is, but I'm gonna take about 80 centimeters. Then we'll will go up from there. So we'll take about 80 centimeters. Point 80. And then let me just copy paste those. And now we'll do the experiment. This time it's going to be a bit boring, but a lot more quiet, of course. So what I'm going to do is I'm going to swing it around 15 degrees-ish. Just use your eyes to measure how much 15 degrees is. The less the better. Well, not the less, but like if you swing 1 degree, something like this, it's hard to measure. But yeah, you know what I mean. So what I'm going to do is I'm going to let it settle. Once it is settled, I'm going to swing it perpendicularly to what the bar is going, so that it swings like this and not like that, right? So now that it is settled, I'm going to count 20 swings, starting around here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and there we go. You get a stop timer at the highest point it reaches. So we got a time of 36.5 seconds. Let's time that in here. 36.05. There we go. Which gives us a period of about 1.8, which should be true. So we'll repeat this 10 times. I'm gonna speed it up, and then we're gonna change lengths. 35.97. Awesome. And now what we're gonna do is we're gonna reduce the length of this by, can I wrap that around here? Nope. So what I'm gonna do, I'm just gonna wrap the string around a couple more times so that it gets shorter. Let me see how I can do that. So I can do something like this. There we go. And then I'll do it again a few more times. There we go. I think that works great. Make sure that this is tight and the tension, no, can hold it. Great. Now this is a lot more than 15 degrees, so I'm just gonna like hold it up until like, oops. There we go. Just gonna hold it until like maybe around here, and then let it swing from there. Perfect. So repeat 10 more times in here. Alright, let's measure the length of this new pendulum. Like I said, we start from where it swings, and then we're gonna go down to where the center of mass is. So we start around here, go down to about right here. The center of mass, I suppose, should be right around there. It's about 48 centimeters, so 0.48. Let's add that 0.48 into our data. A few more times. So let's get started. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 27.88. And there we have it. We have all of these values. And now what we can do is I'm going to show you what these values are. Welcome back to the data analysis lab. And we have filled some of our data here. We have yet to calculate pi, so let's quickly do that. I'm nervous. I just wrote G here. I shouldn't have written G here. So hopefully everything will be fine. So like, let's look at the formula again. G is equal to the square root of this fraction, G times um, t squared divided by 4L. Gt squared divided by 4L, where t is the period, the capital T. And I've also done the same thing down here for the, yeah, same thing here too. So let's replace our G's, and before that, let's find the average pi, which is gonna be equal to the average of this and this. So as soon as we update our code there, we'll be able to see. You know what? Let me just move this around here. I'm nervous. This is a pretty big thing for me, you know? So let's reference this. So G is gonna be, you'll see in a bit what I'm trying to do here. G is gonna be D3, and this guy is also gonna be D3. And average G, so far average pi is 0 because this is 0. Now what I'm gonna do is I'm gonna move this over to here, and whatever G value is, that will, sorry, whatever pi value is, that will be our pi value for pi day. Moment of truth. Hey, it's close, it's very close. Oh my god, okay. I was not expecting it to get this close, especially considering how our G value is twice the accepted, more than twice actually, more than twice the accepted value of current G. And so I was really expecting pi to be like, I don't know, 7.2 something, whatever, 7 over 7. My estimate, my guess was like over 7. But holy shit, holy hell. Pi. Well, there we have it, guys. This is our new value of pi. 4.469. Nice number. 4.469. 522238. Can we extend more digits? Oh, yes, we can. There we go, 10 digits. Oh, this stops there, so let me just remove some. There we go. Yeah. 4.4695222377649500. Those are rounded, of course, so it's rounded to the nearest 5. This may or may not even be a 5. This could be a 4. It could be a 4 something that got rounded to a 5. It could be a 5. It could be either a 4 or a 5. But anyways, regardless, this is our new value of pi. We will be using this for the rest of humanity. We have rediscovered pi again. Alright, hello and welcome back. We found pi pretty accurately, I would say. But first, let's look at something interesting here. This is the equation we found and we used it to calculate pi, but there's something special about it. If you look at it carefully, and if you look at how we used a 1 meter string to make the pendulum, and you may notice that the time period is about 2 seconds because it takes 1 second to get from one side. Let me just draw the pendulum here. It takes 1 second for it to go from one side to the other. This is 1 second, and then it takes 1 second to come back when this is 1 meter. Isn't that a coincidence? Like, I mean, I love the SI unit, everything cancels out because it is defined that way. It is defined that way. 1 meter and 1 second are related to this. It is no longer defined this way, by the way, because there's a few little bit of inaccuracy, but basically the second was defined to be about like this. Basically, if you have a 1 meter long pendulum and you swing it, the time it takes for it to go to the other side is 1 second, aka the period, the time period, the capital T is 2 seconds. If you put it into this equation, we get square root of g multiply time period is 2 seconds. We have 2 squared divided by 4 times the length is defined to be 1 meter. 4 times 1 it looks like a 7. What we're gonna get is gonna be 2 squared divided by 4 is 4. 4 divided by 4 times 1, 4. It's gonna just be square root of g. That's it, they cancel out. So basically, what I mean is pi is equal or approximately equal to square root of g. Because g was defined based on meters and seconds, and meters and seconds are defined based on this pendulum here. It's all circular. The pi is very, very, very close to square root of g, and the reason pi is close to square root of g is not because of a coincidence. It is not the universe being like, oh, mathematics is beautiful. It is not fucking God saying, oh, let pi be equal to the square root of g, or let g equal to pi squared. It is not that. No, it is basically because humans chose g to be based on meters and seconds, and if g was measured in, let's say, feet and hours, it will not be the same. If g is measured based on I don't know, miles and inches and minutes, it won't be the same, right? Square root of g will not be pi if we are using any other measurement systems other than meters and seconds. And the reason pi appears there is because meters and seconds are related by this pendulum. The pendulum of 1 meter swings for 1 second to get to the other side, and another second to come back at time period of 2. That is how meters and seconds were originally defined, and it was scraped, and it was defined by the circumference, by the distance between the North Pole and the equator, I think, and then divided by 10,000. I forgot, but whatever it is, this was the original definition of it, and because of this, it is not a coincidence. Humans made it so that g is equal to pi squared. And so what we can actually do is we can actually find pi by taking the value of our g from experiment number 1 and skip everything in experiment number 2 and just go square root of that value that we found in experiment number 1. Pretty neat, huh? Well, but it's not going to be that accurate anyway, because 1 meter's pendulum does not exactly take 1 second to get there. The period is not 2 seconds, as you can see from experiment number 2. It is a little bit above 2 seconds. But there's a shortcut if you want to get an estimate. We're not going to get an estimate. We're trying to find as accurate as possible. So that is why we did experiment number 2. Well, I guess that was a very neat calculations. So there you have it, guys. We got it. Happy Pi Day. And if you followed along or try to calculate your own pi, congratulations to getting this far. And of course, let me write down our new value of pi, which is 4.4695222 377, our new value of pi right here. Well, happy Pi Day. We are now going to use this value from now on. Thanks for watching, and we will be back with more awesome videos in LygerScience. Stay tuned for our science channel. There's gonna be some more new videos coming up for Liger Plays 2. This video was recorded on Pi Day, which was a bad thing to do because you're supposed to record these videos before Pi Day so that you can upload them on Pi Day. I'm going to be uploading this video one day later, probably tomorrow on March 15, one day after Pi Day. But who cares? Happy Pi Day, guys. See ya.